All right, guys, 6:05. Let's just get started now. Welcome back. Today is going to be our exam 2 review in preparation for your guys' exam 2 coming up in Jeski's class. So, for those of you guys who attended our exam 1 review session, it's going to be a similar format where we'll cover all the essential topics needed for exam 2. Okay. And I know like some topics are harder than others for exams. So what I'll do is, so this exam is going to include Unit 5, stereoisomers, Unit 6, uh, reactions and mechanisms, and then Unit 8, which is all about alkene reactions. So I'm just going to yell out the units, and you guys will tell me if you think it's the most difficult out of the three, okay? And then based off that, we'll allocate our times uh, and just spend more time on those topics, okay? Who thinks that Unit 5 is the hardest topic and would like me to spend more time on it?
Which one is Unit 5?
Stereoisomers.
Stereoisomers.
What about Unit 6, which is all about like reactions and mechanisms, enthalpy, thermodynamics, kinetics, nucleophiles, electrophiles, proton transfer? Unit 6? Okay. What about Unit 8 then? Okay, I see. So majority of you guys think Unit 8's the hardest, which kind of expected. So, okay, so here's what we'll do. We originally, yeah.
I answer all of the above.
Yes, you can. All the above is possible as well. So, but I see that majority of you guys think Unit 8 is the hardest, which frankly it is for this exam. So what we'll do is we've scheduled this session to be 3 hours, but I know 3 hours is way too long. So we'll try to condense it as much as we can and allocate most of our times on Unit 8 instead of 5 and 6, okay? So for these first two units, we're gonna kind of brush through these and not go as in-depth as our usual review sessions, all right? Cool is that cool with everybody? Okay. Before we do, as usual, please scan the attendance. All right. Can you guys give me a thumbs up if you guys filled out that form? All right. Let's get started then. Our first unit, Unit 5, is about stereoisomerisms or isomers. So stereoisomers, these are isomers where all the atoms are connected to the same atom, but the molecule differs in their 3D configuration. So for example here, let me pull out a marker. We see in this bottom two examples, this carbon is attached to 4 different groups, but their 3D configuration differs. They're mirror images of each other, right? So that makes them a stereoisomer. And stereoisomer is very important because using stereoisomers, you can argue about optical activity and the binding to proteins. The first point is relevant to you guys because you guys will do optical activity problems with calculating percentages, enantiomeric axis and whatnot, as you'll see in the next slides. Binding to proteins, this is more specific to biochemistry, which you guys take next year, hopefully. So yeah, so talking about optical activity, let's get into it. Optical activity, all you need to know for this is if a compound is chiral and it's asymmetrical, that's the key word. If it's asymmetrical and chiral, then it's going to be an optically active compound. However, if it's, let's say it has chiral compounds, but it's a symmetric compound, like mesos. Mesos, they have chiral centers, but they're symmetry, right? They have symmetry. So these would be optically inactive. It's only optically active if you have a chiral compound with a asymmetrical compound, okay? So that's the most important thing with this. And then to apply this to calculations, the most important thing on this slide is enantiomeric excess. It's basically stating the it tells us how much of an excess of one enantiomer is in a mixture. So you'll have a mixture of R and S configurations, and enantiomeric excess tells us how much more of one configuration there is than the other. Okay, and the formula here is simplified to EE, which is enantiomeric excess, equals specific rotation of the mixture. I'll just say mixture over the pure enantiomer. All right, times 100 because we're finding the percentage. So let's do a quick practice problem. Let me zoom in for you guys. Do you guys want to do this together, or you guys think you got this on your own? Thumbs up if you guys want to do it on your own, or thumbs down if you want me to walk through it together. Okay, then I'll give you guys like, I don't know, a minute, and we'll come back and discuss the answers. If you need help, ask Alexia or I, and we'll come to you. Okay? In about a minute, so we'll discuss the answers. So it says limited, blah, 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 naturally occurring compound with one chiral center. You see that this chiral center is here. Not that it really matters, to be honest. Question A, Charles obtained a sample that he determined to be 83% of R enantiomer, and the remainder is the S enantiomer. So from these facts, we can deduce that we have 83% R. And if 83% is R, the total has to be 100%. How many S percentage do we have? Just yell it out if you have the answer. 17, right? Thank you. So we have 17% S, right? And this is asking us to calculate the enantiomeric excess, right? So enantiomeric excess, like we said, is the excess of one configuration over the other. And we see that the R enantiomer there's clearly more of it, and there's more of an excess than S, right? So the EE would simply just be a subtraction of these two. Which equals 66%, if my math is correct. Yeah, 66%. So 66% is the enantiomeric excess of the R enantiomer. Any questions on that? No questions? All right. Okay. Next part is asking if Charles mixture is racemic. So racemic mixtures, if you guys recall, it's when there's a 50-50 split in the R and S configuration. It's a mix of 50% R and 50% S. But in this case, we have 83% R and 17% S, right? So it's not an even split of the R and S, right? So that means it's not a racemic mixture. Any questions? Pretty simple, right? Jesky will probably ask you like maybe one, if not two at the most about these excess problems or percentages. So just do a couple of these and you'll be fine, okay? Here's the answer key for you guys. All right, moving on. Chiral centers. These are important later on as we are going to talk about different types of isomers like enantiomers, diastereomers, meso compounds, right? And to differentiate between those three types of isomers, we'll have to know what chiral centers are. So chiral centers are when a chiral carbon, for example, here, is attached to four different substituents, which makes it automatically an sp3 carbon, right? Four different substituents, sp3. So those are just the two requirements you need for a chiral carbon, okay? So if we see here, first example, we have two of the same substituents on this carbon, so it's not a chiral center. Second one, we have four different substituents, and it's all sp3, right? So that make it a chiral center. And then the last one, it doesn't even fulfill any of the requirements. There's only three bonds, three sigma bonds, sorry, and it's sp2 instead of sp3, so that'd make it non-chiral. Moving on. And then isomers, is the important concept is assigning priority. And to do this, we use the Kahn-Engel prelog system where we prioritize the substituents based on their atomic number. Basically, the higher the atomic number, the higher the priority, right? So if we see on the example on the right, oxygen, these two oxygens are higher in priority than this carbon and this hydrogen, right? So these two oxygens would be the highest priority groups. But in the case where you have two of the same priority groups, what do you do next? You go to the next atom on that said oxygen, right? So for example, on this one, we can then move on to this atom here, and it's a carbon, right? But on this oxygen, it's attached to a hydrogen. And we know that carbon has a higher atomic number than hydrogen, so that means this ether over here is going to be a higher priority group. And so on and so forth. If you keep having the same molecules, then you can just keep going on to the next atom to determine the priority. All right. And then special cases, double bonds and triple bonds, they all account for like 2 or 3 carbons. So if you have a carbonyl like this, then it'd be seen as the carbon bonded to 2 oxygens. Or if it was triple bonded, 3 oxygens, okay? Not that triple ones are possible, actually. All right, so this brings us into R and S. You guys probably have done a lot of these practice problems, so I'll be quick with this. What you want to do for R and S, you want to assign the lowest priority group on a dash. For example, here, the hydrogen is the lowest priority group, and it's on a dash, right? That way, it's easiest for us to assign the configuration of R or S. And the general rule speaking is if it goes clockwise, the priority group numbering goes clockwise, that means it's going to be a R configuration, and then counterclockwise is S. Easy way to remember this, R means right. So if you look at a clock, it goes right? The hands. So the R would be the clockwise, and then counterclockwise is S. If you know R, then you're going to know S. Oh, swapping two groups. Okay. So in the case where the lowest priority group is not on a dash, and let's say it's on like a wedge here, for example, what we do here is we're going to assign the R and S configuration as is, and then afterwards, we're just going to switch it. So for example, chlorine, nitrogen, oxygen. Chlorine's the first. So chlorine's first priority group, and then oxygen, and then nitrogen, right? So usually, since it's going counterclockwise, it's an R. But since the lowest priority group is in the front on a wedge, we just switch it to an S. That's the easiest way to deal with these. Any questions? All right. In the case where the lowest priority group is in the plane, for example, 4, what we do is a double cross. Essentially, you're just gonna switch the positions of the wedge, not the wedge, sorry, the dash and the ones in the plane. So you switch 3 and 4 here. And then you do the same thing for the other one on the plane and the wedge. So 1 and 2. And then once you do that, your lowest priority group is going to be in the back on a dash. So then from there, you can assign the configuration of R or S easily. All right. All right. It's pretty self-explanatory. Just assign the configurations for these. I'll give you guys like a minute as well. It's been about a minute, so let's go through these. So A, let's assign the priorities first. So bromine obviously has the biggest atomic number, so that's 1. Hydrogen is the least, so it's 4. And then 2 here on this carbon, and then 3 for this carbon. Because this carbon 2, that sign 2 has another carbon attached to it, so it'd be a higher priority. All right. So we assigned this, but the least priority group is coming out towards us on a wedge. So like I said, the easiest way to do this is assign the configuration as is and then switch. So we see 1, 2, 3 going clockwise. So that's R, but then you switch it to S. So the final configuration would be an S for this. Next one, we see the oxygen would be the primary group, the highest priority group, sorry. And then this carbon here would be second, this would be third, and this would be fourth. And we see that the least priority group, again, is on a wedge. It's literally the exact same as the first problem. So we can just switch it as is, and you get S again. C, we see that the bromine is the first priority group, and then this carbon would be the second, and then this would be the third, and the hydrogen would be the fourth. Hydrogen is coming out at us again, so assign it as is, and then switch it. This case is still going R, and then we switch it to S. So all these are S. Any questions? Any questions on how I like switched from R and S or anything? Nope. All right. Yeah, so here it is. Answer keys. Um, okay, more assigning. I'll give you guys another 30 seconds or something. Be quick with it. Uh, first one, assign the priority. This will be first priority. This would be the second. This would be the third. And this hydrogen would be the fourth. Same pattern as the last three where the least priority group is in the front. So assign it as is. This one's going counterclockwise, so S. And then we switch it, flip it to R. So this would be an R configuration on that chiral center. If we look at E, the chiral center in question is here. And we'd assign this hydroxyl group as 1, and then this ketone as 2, and then this hydrogen as 4, and this carbon as 3. So in this case, the least priority group is in the back, so we can just assign it counterclockwise again. So this is just S. Last one, this chiral center here is, by the way, this is not a chiral center, even though it's on a dash, because we have a methyl here and a methyl here. And we said that we need 4 different substituents for it to be a chiral center, right? So that's a false chiral center. It's not even false, it's just not a chiral center. So assign 1, 2, 3, 4. Okay, this is the one where the least priority group is in the plane. So what we do is a double switch. We want the least priority group in the back, so we're going to switch this hydrogen with the oxygen. So you get hydrogen on the dash, and then you get this oxygen on a plane. So we switched 1 and 4, if we see. And then we switch the exact same for 2 and 3. So 3 would be on this plane, and then 2 would be on a dash. So if we do this now, it's going clockwise, right? So that would be an R configuration. Any questions? Okay. Let's move on then. RSR. Yep. All right, this brings us to the next topics about enantiomers, diastereomers, mesocompounds, like I mentioned before. So enantiomers, the only difference is that every chiral center is swapped. So if it was an R in one isomer, then it's going to be an S in the other one, the enantiomer. If it was like an S, then it'd be an R. If it was RR, SS, SS, it'd be an RR, etc. Examples right here. Diastereomers, it's close to being an enantiomer. It's just that almost every chiral compound swaps the configuration except one or a couple. So if it was like a RS, then it switched to a RR instead of a SS. Sorry, SR. And that making a diastereomer. If it was an SRB and SS, like etc., right? Just one chiral center that stays the same or changes. And then mesocompounds are, they have chiral centers, like I mentioned, but they have a plane of symmetry, right? So that makes the entire molecule an achiral compound. So yeah, easiest way to identify meso is if it has a plane of symmetry. Okay. And then nomenclature, um, this is pretty easy. It's just the alkane nomenclatures that you guys have been doing since last exam, except you just add the locant for the stereoisomers and the R and S configuration like we just talked about. All right. So let's do practice problems identifying the relationship between these couple. I'll give you a minute again. Um, Minutes up. Let's go through these. So easiest way to compare the relationships is compare the stereo centers. So this stereo center here, you can assign it as uh 1, 2, 3. So this would be an S. This one here, 1, 2, 3 is going clockwise, but the least substituent group is in the front, so we switch it. So this would be an S. So these would actually be identical molecules since they have the same chiral center. Because if you think about it, you can kind of pancake flip it over and it'd still be the superimposable image. All right. B, we see that everything, all the stereo centers are the exact same except for one, which is this phenyl group, right? And if we said all the stereo centers are like the same and one's different, that means it's going to be a diastereomer, right? So this is a diastereomer. And then C, um, telltale sign is if you hold a mirror here, we can see it's literally a mirror image of each other. So that'd make it a enantiomer. But also you could assign R or S and then compare it and see if it's flip-flopped. And that's also a telltale sign if it's a enantiomer or not. Any questions? Okay. Is a key. Okay. In this case, we're asked to draw the molecule based on the relationship that is given. So I'll do like one example with you guys. So it's asking us to draw an enantiomer. The easiest way to do that is just draw the mirror image. Imagine there's a mirror here. So the F would be like this. Hold up, I switched. And that'd be an enantiomer.
Another way you could do that, if it's just like this, you can just flip the dash and wedge. So you put like F on the wedge
Oh, that's
and the
true.
OH on the dash.
Yeah, what he's saying is just flip the wedges like this. That's also another way. That's probably actually easier. Just do that. Okay. Yeah, do the next two. I'll give you like 30 seconds. Actually make that 20. Also, it could be possible that you can't draw the enantiomer or diastereomer. So if you can't, then just put not possible. All right, enough time. Let's go through the answers. So actually, let's just go through these. The first one, it asks us to draw an enantiomer of this second molecule, but you can't actually draw it because this is a meso compound. So if you can see it right here. The single bond here, it can actually rotate, and you'd get something like this. Uh, And as we see, there's a line of symmetry right here. And there's a chiral center, right? So a chiral center, but there's a line of symmetry. That fits exactly the definition of a meso compound, right? And meso compounds you can't draw an enantiomer of. So you put not possible. All right. And then diastereomers, this is probably the easiest one to sketch out. You just change one of the stereocenters. So I'll change this one. You can change the other one, but up to you. Uh, so instead of the hydroxyl grouping on the dash, I'll make the ethyl group on the dash and the OH group on the wedge. And that's a valid diastereomer structure. Yep.
You just put them all on the same plane, or is that the?
What do you mean on the same plane?
Can you just make them all wedges or all dashes?
That's not possible because we said chiral centers, they're sp3 hybridized, right? 4 bonds. That means it's going to be a tetrahedral structure, so only one of them can be behind the plane. You can't have two substituents behind the plane. That's just not geometrically possible because of the bond angles, the specific bond angles. Any other questions? All right. Yeah. Okay. All right. We're going to move into cis versus trans. So cis versus trans, it's not specified here, but cis versus trans only works when you have two of the same identical molecules on like a double bond, let's say. So these two are identical and they're on the same side. That means it's going to be cis. If it's on the opposite sides like this, it's going to be a trans, right? So for these, yeah, just do that. It has to be two of the same identical molecules. And it doesn't have to be a double bond as well. You can have like a cyclo ring structure like this. And then you can tell whether it's cis or trans because two of the same substituents are on the opposite sides. So this would be a trans. All right. In comparison with E and Z, it's a similar concept, but much broader. And these are only specialized for double bonds. And to assign priority for these E and Z isomers, we have to use the Kahn-Engel prelock system that we use for RNS in the sense that the larger your atomic number, the higher the priority. So the two highest groups are going to determine whether it's going to be E or Z. And E is going to be when it's opposite sides. Z is going to be on the same side. Pretty lame, but easy to remember, okay? Um, yeah. So like I said, E and Z is a much more broader system than cis and trans. So you can use E and Z to describe cis and trans isomers, but you can't use the other way around where you use cis and trans to describe E and Z. Okay? So yeah, when in doubt and you can't decipher whether to use cis and trans or E and Z, just use E and Z for safety. Constitutional isomers is the last type. And this is just saying if you have the same molecular formula, but you have a different molecular representation. See, all these have C6H14, but their molecular structures are all different. All right. So let's do some practice with the cis trans versus easy. These are easy, so actually I'll just call you guys. Who wants to do the first one? Any volunteers? Uh, yeah, it is Z because the two of the highest priority groups, is going to be this fluorine and this carbon, right? There's a hydrogen here, by the way. You just can't see it. So these are the two lowest and these are the two highest. Two highest on the same side. Same side, Z. This ugly Z. Volunteer for the next one. Yeah. Cis. Correct. Next one. Any volunteers? Alex? You're oh, okay. Any other volunteers? Yes, it would be E because the two highest groups are on opposite sides.
What makes the one left highest?
This one?
Yeah.
So this one has a hydrogen here as well. And this one as well. And we see that of these two, the carbon has a higher priority group, right? Yeah. So that would be E. What about the last one?
Z.
Z? Yeah. Actually, we said for E and Z systems, we can only use it for double bonds, right? So yeah, Alex, what would it be? Yup, it'd be cis. Because E and Z systems can only be applied to double bonds or alkenes. This is not a double bond, right?
Isn't cis also rounded up and down?
Yeah, you can do that. Cis and trans can be double bonds, but they have to be identical substituents.
There's no double bond there.
Yeah, there is no double bond, so we can't use E and Z here. E and Z is only for double bonds. Any questions? Yep, you. Yeah, of course. So a trans version would look like this. And just draw this chair. Sorry for my ugly chair, but so one is going up and then the other one would be going straight down. So that would be an example of a trans isomer. An easy way to do this as well is you can convert these chair structures into a cyclohexane ring. So for example, you can make this like this, and one's going up, so that would be on a wedge. The other one's also going up, so this would be on a wedge. And since they're both going up, that's a cis.
So typically cis and trans is only across a double bond, but in this case, it's across a single bond because it is a ring and a ring cannot rotate. So if it was just a single bond with those two groups, it could really just rotate any way at once because single bonds can rotate. But because this is a ring, that's why you can determine if it's cis or trans.
It's a good point, actually. Yeah, so if you can rotate it like that single bond, then you can't use any of the systems. Any questions? Yep.
Distinguishes C from E. Is it because there's a fluorine on that molecule?
Yeah, so yeah, E and Z has to do with so Z is when the highest priority groups are on the same side. And if we see from the first example, there's a hydrogen here. The highest priority groups are going to be this fluorine compared to this carbon, and then this carbon right here, right? And since the two highest priority groups are on the same side, that means it's going to be on the same side. All right? Make sense? You think so?
I think so. I think it makes sense.
So yeah, E is just the opposite, since we have the two highest priority groups on the opposite side of the double bond.
So it's all in relation to the double bond.
Yes,
Okay. Then that makes a lot.
whether it's on the opposite sides or on the same sides.
What do you mean the same side for the first part?
So we see here, it's because it's tilted. I'll show you a non-tilted. So this is our example right here, right? And our highest priority group is going to be these two molecules. And they're on the same side of the double bond. If it was the opposite, like this, Then the two highest priority groups would be on the opposite sides, right? Does that make sense?
Yes, and then
Yep. All right, Z cis, E cis. All right. So that concluded Unit 5. Let's go over thermodynamics and kinetics now. So chemical reactions include bond breakage and bond formations, and that comes in the form of energy, right? Called bond dissociation energy. And we can measure this energy using enthalpy. And these energies can be quantified using this chart in kilojoules per moles or kcals per moles. So if you're given like a reaction like this and asked to find the delta H, you just want to identify all the bonds broken and bonds formed. So the bonds broken, let me just pull the answer key. Bonds broken, we see that this carbon-bromine bond is cleaved. So that's broken. That's 272 kilojoules per moles. If you look at the table. And then this H2O group is also cleaved. So that means this would be a 498 kilojoules per moles. And then bonds formed, we see that this carbon and this oxygen form a bond, and that bond is 381. These are negative signs, by the way. It's just to list them out. And then HBr, bromine bonds formed, so that's 368. So add up all the bonds broken and then subtract it from the bonds formed. And you get 21 kilojoules per moles. Simple, right? Any questions? He probably won't ask you any of you guys this type of questions, if I'm being honest. Yeah. So enthalpy obviously relates to heat, right? Heat energy. So we'll be talking about exothermic and endothermic. You guys probably know this by now and heard of this multiple times in general chemistry, biology, right? So exothermic is when it's negative and the system is losing energy. Positive is when the system gains energy. Simple. So quick question. Is this diagram endothermic or exothermic? Correct. Because the delta G, or delta H is positive. All right, and enthalpy can be related to delta G as well, like I mentioned. And similarly, like what was it? Exothermic versus endothermic, we can use exergonic versus endergonic for Gibbs free energy. It's the same trend. If it's a negative delta G, it's going to be exergonic. If it's positive, it's going to be endergonic. And Gibbs free energy measures the free energy in a system and measures the spontaneity. If it's exergonic, that means it's a negative delta G, so it's going to be a spontaneous reaction. If it's a positive delta G, that means it's endergonic and it's non-spontaneous. All right, so that was talking about the thermodynamics of a reaction. Kinetics is a whole different thing. Kinetics, like the name suggests, is the measurement of speed of the reaction. And we can quantify this into an equation like this, where rate equals K times the concentration of the starting materials, K being the rate constant. And the larger the rate constant, the faster the reaction. All right. Kinetics, three main factors that affect the rate constant K. It's temperature, energy of activation, and sterics. Temperature makes sense because if you increase the temperature, that means the molecules will have more kinetic energy and they'll collide at much faster frequencies. So that'll increase the rate of the reaction. Activation energy, if you decrease it, that means you have to put in less energy for the reaction to proceed. So that also increased the rate of the reaction. Sterics is talking about the geometry of the molecules, because the molecules have to be in certain orientation for the collision to have any products formed. So those are the three factors. Any questions? All right. So yeah, like I mentioned, kinetics is all about speed. Thermodynamics is about spontaneity and delta G. So you can compare these two using the values from a energy diagram like this, where you can use the EA to predict the kinetics, and you can use the delta G or delta H to determine the thermodynamics and whether it'll favor one or the other. So here's a quick problem for you guys. I'll do the first one with you guys. We have products A and B going to C, D, or E, F. It's asking us to find the thermodynamic and kinetic products of both. Of this reactant, sorry. So if we look from a thermodynamic lens, it's all about delta G. The delta G here for product C and D is the greatest compared to E and F. And we said that the greater the delta G, the greater the spontaneity, and the more thermodynamically favorable it is. So C and D would be thermodynamically favorable. And then for kinetics, it's all about the activation energy. We see products, the blue line, the activation energy is less than the red line. So C and D would also be kinetically favorable. I'll just ask you guys then for the next one. Do you think C and D or E and F is more kinetically or thermodynamically favorable? Let's start with thermodynamics. Who thinks C and D is more thermodynamically favorable? What about E and F? For thermodynamics? Remember, thermodynamics is all about delta G. So whichever one has the greater delta G is going to be more thermodynamically favorable. So in this case, C and D has a greater delta G than E and F. So in terms of thermodynamics, C and D would be more favorable than E and F. On the opposite spectrum, kinetics-wise, E and F has a lower EA than C and D, right? So products E and F would be more kinetically favorable. Does that make sense? He'll probably ask like one of these type of questions. If not, actually, I don't even think he might ask this. There's a question like that on the quiz. Yes, stability is asking about the thermodynamics, and then faster, it's all about kinetics.
Also, the one that has the lower energy in the product that's more stable.
Yeah. So when we look at energy diagrams, we can use transition states and intermediates as well. Transition states is the higher energy state, and intermediates are the lower energy states. So the peaks are going to be the transition states. Intermediates are going to be the lower transition states. All right. So from here, we can tell that the peaks here are 1, 3, and 5. So those would be the transition states. And then 2 and 4 are going to be the intermediates. All right, Hammond postulate is basically relating it to transition states. Transition states the highest point here. And whichever side the reactants or the products is closer in energy to the transition state is going to is going to resemble closer to that structure. So for example, here, the transition state is closer to the reactant side than the products in energy. So that means this transition state will resemble more of the reactants than the products. All right.
Yeah.
We'll switch now. Alexi will cover the rest of this.
How are we feeling? Y'all feel like y'all need like a little break? Or y'all want to keep going? Thumbs up for a little break. Thumbs down for keep going. All right, we're gonna keep going then. All right, so we're gonna start getting into nucleophiles and electrophiles. An electrophile is something that is electron deficient and can accept electrons. Basically, they really want them. They're very greedy for the electrons. They need them. And a nucleophile, they're breaded. They got so many electrons, they want to give it to everyone. So we see electrophiles typically have a positive charge, and nucleophiles typically have a negative charge. Also, double bonds can serve as nucleophiles. So in this practice, just square around the nucleophilic centers and circle around electrophilic centers. Give y'all like a minute to do this. Let's go over this. So an electrophilic center can also be when a more electronegative atom is bonded to a carbon, like in this double bond right here. So this oxygen is pulling away electrons from that carbon. So that carbon actually becomes an electrophilic center. This can also be seen through the resonance where this will occur and it will form this. Okay. And then on this nitrogen, the nitrogen has lone pairs that it can give. So it makes it a nucleophile. This positive charge typically associated with electrophiles. So we can circle that. This is another case where the oxygen is pulling the electrons toward it. So that makes it nucleophilic because it's pulling electrons. And the sulfur is having its electrons pulled away. So it has a partial positive charge, and that makes it an electrophile. Any questions? Cool. Next, we're going to go over carbocations. Carbocations are formed as intermediates in some reactions. The stability is based on the amount of substituents and resonance it has. So if it has more substituents, for example, in this tertiary, it's more stable than, say, a secondary, primary, or methyl. And by substituents, we're talking about the amount of carbons that are attached to that carbocation. This is basically showing molecular orbital theory. It's not too important. Just know that more substituents is more stable. This is an example where resonance is influencing stability. So more resonance means it's more stable because that charge is distributed across the molecule. Also, electron donating groups can stabilize a carbocation, whereas electron withdrawing groups can destabilize it. So an example of an electron donating group is carbon chains. That's the most common example you'll see. Carbon chains attached to a carbocation is going to donate some of their electrons and make it more stable. An electron withdrawing group, that would be like an oxygen. That oxygen is going to pull it. All right, there's a little example. Just rank the carbocations from most stable to least stable. Give you like 30 seconds to do this. All right, let's go over it. So we can automatically see that B is primary. It was only attached to one carbon. So that's automatically going to be our least stable. And then next, we're going to compare A and C. They're both tertiary. So the second thing that influences stability is the resonance. A can do this resonance to form this. Which means that the charge is spread across the molecule and it's less concentrated in one place, making it more stable than C. Make sense? Very simple stuff. Next, we're going to go over mechanisms and their patterns. By the way, if y'all have a question during when I'm speaking, just raise your hand and June will come help you. So basically, with reaction mechanisms, you always want to start your arrow at a source of electrons. So that can be a double bond or a lone pair. And then that is going to end at a electrophile. Here's an example of that. We got the nucleophile, the bromine, attacking the carbocation, which is our electrophile. And this is called a nucleophilic attack. There are 4 essential patterns that you need to know, and this is one of them. This is our next one. It's called loss of leaving group. It's when there's a good leaving group, like bromine, it is able to detach from the molecule, and usually it forms a carbocation and then the bromine by itself. This is our second of the 4 important patterns. Next, yeah. Yes, yes. If it's something that's like going to be unstable when it leaves, it's not going to leave. So our next one is proton transfer. This is like a specific type of nucleophilic attack. It's when a nucleophile or something with electrons is going to attack an H or hydrogen. Hydrogen, H plus is also called a proton. So in this case, the O or the oxygen is attacking the H from this H3O and it takes it. It's called proton transfer. Proton being transferred. And then the last one is rearrangements. So we could have a hydride shift. This is typically done to cause a carbocation to be more stable. So like in this case, it is secondary. And then over here, it becomes tertiary, becomes more stable. So this will always happen because it makes the carbocation more stable. So there's a hydride shift. That's when a proton is able to shift. A hydrogen is shifting. We see that in the hydride shift example. And this can also happen with methyls. Do not forget about the methyls. They love to throw that in to trip you up. The hydride shift people usually get, but the methyl shift, like people miss that in Orgo 2. I miss that in Orgo 2. I miss that in Orgo 1. It's one that people forget about all the time. All right, so for this, you're just going to label the pattern that is being used. Give y'all like 2 minutes to do this. I'm going to write out the patterns. Yeah. All right, let's go through this together, actually. So for A, what pattern is that? Yes, also known as rearrangement. Sometimes you'll see it abbreviated as RE. What about for B? Yup. And C? Yes, there's a proton transfer, abbreviated PT. D? Yup. Oh, they're pretty good at this. And E? Even group. Yep. Nice, nice. All right, and then for this portion, draw the rearrangement that will occur. Most of y'all got this, so let's go over it. So for this first one, we can do a methyl shift like that, and that will form this structure. And some of y'all might ask, that's a secondary cation going to a secondary cation. This triangular ring the molecules are very close to each other because of the angle, and that is less stable than them being a square like this. That's not super important. He probably will not ask you something like that. And then for the second one, we can do a methyl shift to form this. Or you can do a hydride shift to form this. There should be positive charge here. Makes sense. And then for this one, you can do a hydride shift to form that. And then for this last one, you can do a methyl shift to form that. Makes sense? Thumbs up, we get that.
Stabilize next to benzene.
Does that take priority over the tertiary? I don't know. Isn't tertiary like?
I thought so.
Yeah. I'm not gonna correct that. For this one, it might be that the secondary is more stable than the tertiary because this can do a lot of resonance, but we're not exactly sure on that, so that might be something to ask your professor. Yes.
The first one about hydride shift, the nitrogen is happening to something for the tricycle. It's on the,
Talking about like that.
and then it would be attached to the other.
Yeah, I like that one. I don't see anything wrong with that. Right?
Yes. I guess torsional strain is more important in this case. I don't know.
Yeah, if you get something like that on your exam, you should do this. This is more of an Orgo 2 concept. It's not that important for now. That's a good thing to point out. Answers. This one, a little unsure about, but we'll probably do the hydride shift.
Can you write up the resonance and have that as your answer instead?
You're talking like the resonance like that. So I probably would not do resonance with that because that is a benzene ring, and typically this is very stable by itself. So if you break it and form like that, like it's a little less stable, but not super important. That won't be asked. All right, for this, just label each step of the mechanism using the patterns.
I feel like they got this. You can just scale.
All right. Y'all probably got this. So let's go over this. First step, we have a nucleophilic attack going on right here. Because remember, this is a partial positive right there. And then in the next step, this is a proton transfer. Because that proton is going from one molecule to the other.
Goes down and then to the right. So you got to do this.
Okay, I see. And then from here to here, this is a proton transfer because we see that H group is now on what was the O minus. And then we see that this arrow shows the OR being kicked out. So that is a loss of leaving group. And then this should go this way. We see that this H is going on that OR, which is seen here, and that is a proton transfer. We can go through this one together. So this first step, what do we think that is?
Proton transfer.
Yeah. And then the second step? Oh, you're talking about this? Yeah. Remember Jessica wanted them. To wait a
That's
bit.
true.
And then the next step. Yeah. Yeah, y'all got that down. All right, we're gonna go over alkene reactions. This is the stuff that you said was the hardest. So if you have questions on this, please raise your hand. We'll be happy to help. So regioselectivity, basically, it's where the reaction wants to go. So in this case, we're looking at this. Acid catalyzed hydration and hydroboration oxidation both put an OH group across the alkene, but they differ in which side of the alkene they put it on. So we see that the acid catalyzed hydration is going to put it up there, and the hydroboration oxidation will put it over there. So it's either Markovnikov or anti-Markovnikov. Markovnikov is it adds to the more substituted carbon. So we see that here, that is Markovnikov. That OH group is going on this more substituted carbon. And then we have anti-Markovnikov, where the nucleophile is added to the less substituted. And we see that with the hydroboration oxidation, where it adds to this less substituted side of the alkene. Then we have stereoselectivity. So reactions can either add syn or anti across the double bond. So syn is them being on the same side as or same side. So they'll either both be up or both be down. And then anti is when they're either one up, one down, or flipped. And then some can be both. So that is stereoselectivity. So this just illustrates regioselectivity versus stereoselectivity. So in this case, regioselectivity is where this OH is going on the double bond, either on the bottom or the top of it. And then stereoselectivity has it either on a dash or a wedge. So this is the first of the alkene reactions. The alkene reactions are just something that you have to memorize. This is something you got to put into practice and memorize on the exam. It's something that you'll be expected to know. So hydrohalogenation, it is with H and a halogen. So that halogen typically is bromine or chlorine. That's what you'll see most often. And this is Markovnikov, meaning it's added to the more substituted side. We see that here. And then the stereoselectivity, it can be either syn or anti. And the intermediate is a carbocation. This is one of the mechanisms you should know. You don't have to memorize all of them, but this is one that you should memorize.
Also take note that since you can form a carbocation as an intermediate, rearrangement is very possible.
Yes, keep that in mind. Could rearrange. Next, we're going to look at acid catalyzed addition of water. This is Markovnikov, so it's added to the more substituted side. And then this one can be syn or anti and has a carbocation intermediate. So we see that H2SO4 and H2O will add the OH to the more substituted side of the alkene. This mechanism you should also memorize. Next, we're going to look at acid catalyzed addition of alcohol. This one is Markovnikov. It's pretty similar to this one, just instead of H2O, it's ROH, R being like, say, like a methyl group. So this could be, or an ethyl group, it'd be like that. Pretty much same thing as last one. Markovnikov can be syn or anti, and it has a carbocation intermediate. This one is hydroboration oxidation. This one is anti-Markovnikov. So it's going to add that OH on the opposite side, and it is syn addition. So that means it's on the same side. It's going to add an H and an OH on the same side. And this mechanism is not one that you need to memorize, but do memorize these reactants and the products that they give. This is a mechanism. He's not going to ask you about this. Then we have halogenation. This is Markovnikov, and it's anti-stereoselectivity. So we see that one bromine is up and one is down. Could also be like this, like the same thing. And this is the mechanism. This is one that you should memorize. Then we have halohydrin formation. So what this one does is it's kind of like Markovnikov. It's going to add the bromine or whatever halogen it is to the less substituted side. So we see that this bromine on the less substituted side. And then it's going to add an OH if it's water or an OR if it's something else to the more substituted side. So we see that in this case, it's MEOH that gets added OME to the more substituted side. And this is anti-addition. So we have the OME going down and the bromine going up. This is a mechanism you should memorize. You should memorize this one. This is epoxidation. So it's MCPBA and it forms this epoxide. This is going to be SYN, so can also be that. Just make sure you're on the same side. This mechanism is not one that you have to memorize. Then we have reductive ozonolysis. Basically what this does is it cuts the double bond and then puts oxygens there. So what it's going to do is cut this so it looks like that, and then it adds oxygen there. And that is basically the same thing as that. When I took the class, he didn't care if we wrote it this way. Just cut that double bond and add oxygen. And that is represented by O3 at negative 78 degrees Celsius, then ZnH2O. And make sure you number these steps. The numbering is important. So you want to label these 1 and 2. This is SYN dihydroxylation. So this uses OSO4, and then it's going to add OH SYN to the double bond. This is not a mechanism you need to memorize, but do remember these reactants and make sure you number them. Don't forget those numbers or else they'll take off points. So we see that the OH is added across that double bond and they're on the same side. Next, we have catalytic hydrogenation. So you use H2 and then use a catalyst. In this case, they're using palladium. So there is no regioselectivity. It's just adding H to both sides of the double bond. And the stereoselectivity is SYN. So the H's will both be on the same side. All right, got some practice here. Give y'all a couple minutes to do these. And we'll go over them together. Go over these. So we know that OSO4, NaHSO3, H2O, what that does is it adds OH to both sides of a double bond in anti-addition. So we know that there is a double bond here. Draw that better. Something like that. OSO4. My mistake. So OSO4 actually adds it in SYN addition. So what this would do is it would add it to the same side. First like this. And then this answer is it rotated around this bond right here. So it looks like something like that, which resembles our product. So this is anti. And then O3, ZnH2O, we know that what that does is it cleaves a double bond and puts oxygens there. So that will look like that. Because if we cleave these, it will give us that and that and this. All right, and then for this HBr, we know that this is going to add bromine to the more substituted side. So what that looks like is it's not a chiral center because there are two methyls, two of the same group. And then we get a bromine here. And then it could also be also get that as an answer. All right, we're gonna have y'all draw the products of these. This is MBS. Go over this. So in the first case, Br2, we know that is anti-addition across a double bond, adds two bromines. So we can draw out this molecule. Without the double bonds. And then we know that get a bromine there. And we get bromine there. And then over here, we get a bromine there. We get bromine there. Get that? Br2 adds two bromines and they're anti. For the next one, MBS, what MBS is going to do is add a singular bromine on the less substituted side of the alkene. So first, that's going to form something like this. And then recall that an OH group can then be used as a nucleophile to attack that positive charge. It's the same as this. So that OH group on that example is the same thing as this MEOH right here. So what that is going to do is it's going to go over here and it'll form a structure that looks like this. All right, and for the next one, H2SO4, H2O, what that does is adds OH to the more substituted side. So in this case, the answer will look like that. Answers. And then here we have some more practice. Give you all a few minutes for this. Hmm? This one.
We have to do that next. Oh,
This type of stuff will most likely be on your exam. He'll probably ask questions just like this one. All right, let's go over this. So we see that when it's asking for the reactants, what you want to do is compare the products and like your starting material. So we see that this bromine is added and there's no more double bond. So that means it was HBr that did this. HBr adds bromine to the more substituted side of the alkene. And then for this example, we see there's a bromine and there was HBr. We know that HBr adds bromine to the more substituted side of an alkene. So we're going to draw this out like this. And we put that double bond right there. So that when HBr comes, it will go on the more substituted side of that alkene. It will go right there and we'll get this product. And then here, we see that where there was a double bond, there's now an OH. And the reactants we use for this are OSO4 and then NaHSO3 H2O. There is syn addition of OH across that double bond.
Do you guys know what we'd use if it was an anti-addition? If it was an anti-addition, we'd use MCPBA. NH3 O plus.
So for this type of product, you'd use MCPBA and then H3O plus. And then for the next one, we know that Cl2 typically adds 2 chlorines across a double bond, and they are added in anti-addition. So we see here that they are syn. So what we can do is we can redraw it with this bond rotated. It'll look something like that. So drawing that out, we know that chlorine adds across the double bond, so we can just put a double bond between them. It'll look like that.
One too many carbon.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. I have one too many carbons. On, that's the answers. All right, we're gonna have you do some more practice. Give y'all a few minutes for this. The way I recommend y'all memorize these reactions is probably make a Quizlet. That's what I did when I was taking the class, is I made a Quizlet with it'd be like the reactant and the product, and the answer would be like what would make that product. So that's how I studied for this. Y'all want to go over this together? Thumbs up. Okay. So HBr, again, it's going to add bromine to the more substituted side. And what that will look like is that.
This isn't stereo sample because it's even on both sides.
Oh yeah, you're right. That's my mistake. This is not a stereo center because both this group and this group are identical. And then next we have H2 palladium, and we know that that adds a double bond. It turns a double bond into a single bond. So where we see there could be a double bond, we can redraw that as a single bond. Or we can draw a single bond as a double bond. So if we were to redraw this, it would look like going up, down. Look like that. And then we could just insert that double bond right there, and it would get rid of these stereo centers. And then this molecule, that is MCPBA. And we know that MCPBA, it turns this double bond into an epoxide. And what that looks like is it forms this little triangle with the oxygen. It can also be this, but these two compounds, they have stereocenters, but they're symmetrical. There's a little plane that goes through there. So they're meso compounds and identical. So we can cross one of those out. Key. Thumbs up to go through these together, or thumbs down, y'all want to try them. All right, we'll go through these together. HCl, just like HBr, is going to add a chlorine to the more substituted side. But remember, there's a carbocation intermediate. So the first thing that happens in the mechanism is that the H goes on the less substituted side and forms this. And then we can do a methyl shift to get something like this. And then we have that Cl minus still, and it'll attack right there to give us
Methyl group still. To do methyl transfer.
got that methyl. It will give us something like this. All right, and then for this one, MCPBA, we know that that forms this epoxide across a double bond. So we can redraw that without the epoxide. Instead of the epoxide being there, it will be a double bond. And that looks like that.
Notice how even though the benzene ring has double bonds, it's still not affected by the reactants, right? So these benzene rings, they're very sensitive. So not sensitive, they usually won't react with these type of reactants. And this is more like an Orgo 2 concept. So whenever you see a benzene ring with an alkene in it, don't touch it. It can't do any reactions.
Y'all won't learn any reactions that can happen on the benzene ring. All right, and then for the next one, we have the O3ZnH2O. And we know what that does is it cuts that double bond, puts a little slice through it, and puts it oxygens there. So what that looks like, something like that. Just gonna slice it open. He's typically okay with you drawing it like this, but if you want to make it look like organized, also draw it like this. It's the same thing. It's the key. And here we can get feedback.